All right, looks live to me. All right, I'm Brian Ray. I'm the CTO and founder of Link Labs. I'm joined here by Mark Lakel, one of our wireless engineers who I promised would not have to appear on camera much, so I'll keep it pointed at me. Thanks for joining. I am going to basically share slides and chat, and we'll get into that here. So let's fire this up. Apologies. I've not used YouTube for webinar before, so it's a learning process. All right, that's trippy. All right. So this is one of our first webinars that's a little bit more specific in a given topic than just a general overview of the space or talking about Link Labs. And one of the topics that we've been dealing with a lot here at Link Labs, and certainly Mark has been experiencing that, is using Bluetooth, and specifically Bluetooth Low Energy, as a hybrid between sensors and other networks like Symphony Link or LTE networks or Wi-Fi or other things. And we'll get into those details here. I love answering questions, and so if you have a question during the webinar, Mark is tuned in over here on our forum site. So just head on over to the forum.link-labs.site, quickly sign up, and then just click new topic up here, and then you can just leave it in general IoT discussion, and we'll see that come up. So feel free to chime in with discussions, and hopefully we'll see questions as they come up. Okay, I'm just going to jump right in and talk a little bit about Link Labs. Link Labs is a company. We're based in Maryland in the US, and we see our business in three different buckets. The first, which you may be familiar with, is Symphony Link, which is an industrial or enterprise low power wide area network system. And it's often used instead of technologies like Wi-Fi or Zigbee to cover large facilities, city blocks, campuses, factories, to connect to sensors and controllers for various IoT type or telemetry type use cases. Another line of our business that we're excited about and partnered with Verizon right now on is LTE Cat M1 connectivity. I'll get into what we're doing there, but that's certainly got us busy today or these days right before the launch of the LTE Cat M1 network on Verizon. And finally, our product AirFinder is actually based on Bluetooth and Symphony Link at its core, so it's very apropos to this discussion. And it is a real-time location system that's based on Bluetooth, Low Energy, and Symphony Link. Any questions yet? Nope, good. Symphony Link is at its core an LPWAN system, which is a gateway-based system. We also have repeaters that nodes can connect to, but we have indoor and outdoor gateways that connect over long range using UHF, so that's 900 megahertz in some countries and 860 megahertz in other countries. And we enable a lot of features like high scalability, message acknowledgement, firmware transfer. I'm not going to get into the nuts and bolts of Symphony Link, maybe a little at the end, but this is the core wireless architecture that we often use in combination with Bluetooth to really leverage the cost and performance from battery life or other use case drivers out of these IoT systems. A new product that we're coming out with here, which is again very germane to this discussion, is an LTE-M Bluetooth bridge device, which you can see a prototype pictured here. This combines Bluetooth central device with an LTE IP backhaul. So you can do things like connect to a bunch of Bluetooth peripherals in a setting where you might otherwise have to use a mobile phone. So very powerful architecture, and you can really get great battery life on devices like this, which open up a lot of use cases for Bluetooth, specifically in the industrial enterprise setting, which we'll get into. Other things that we're doing in LTE-M, just for your education, that platform that you saw for Bluetooth is extensible to other types of sensors. So we have GPS, IO, motion, environmental sensors, and it's very modular, and we're working on getting the software libraries built out so that you can easily communicate right off the shelf directly to the Verizon network to do these simple sensor and controller devices. LTE-M is the first time that a long life battery powered sensor can be directly connected to cellular and not run out of battery batteries in a matter of days. And we'll make these slides available as well to anybody that wants them, so don't fret. And some key takeaways on Cat M1. Again, this is, I'm not going to spend a whole lot of time on this, but this is a version of 4G that adds the capability of simpler and lower cost devices to connect at about 100 kilobit per second max to the core network to exchange IP data. It's being tested right now and will be deployed certainly by the middle of this year, if not even earlier, on Verizon. I know AT&T has also made announcements about probably a little bit later in 2017, at least in the US. Oh, somebody was saying that the fonts on the presentation aren't clear enough. I apologize. Again, this is a experimental use of YouTube, so I appreciate that feedback, and we'll make the slides available afterwards, so apologies there. Module costs for LTE-M, generally probably around the $15 range, so at least half of what a traditional Cat 4 or 3G data modem might cost. And data costs for under a megabyte of data in the $1 to $3 range per month. You know, there's a couple of different flavors of Cat M modules that are coming out. I think it's important to make sure that you're not using a refactored Cat 1 modem that, you know, has a Linux core and long boot times to come out of power saving mode. We're specifically working with Sequans chips in our solutions, and we're very happy with that. A little bit about NBIOT. NBIOT is a different cellular standard than LTE M1, specifically for IoT type devices. They come at the problem from a different angle. I don't think that this is going to be deployed in the US, at least in the next few years, because there's some base station compatibility, spectrum issues, and other things that make this better suited to countries with you know, large 2G footprints that they're trying to reband, et cetera. But it's a 200 kilohertz channel bandwidth up to about 144 kilobit per second uplink. And it's a half duplex system, meaning that the modules can be very simple. I think the chipsets could potentially be slightly less than LTE M1, but I don't think significantly so. So I still think you're looking in that $10 to $15 range, but certainly a technology to keep your eye on as well. You know, LTE-M is really stripped down 4G, LTE Lite I call it, and NB-IoT is really bolting on a lot of capability on top of more traditional, simpler, low power wide area networks. Something like Sigfox or others have been the genesis there. So they're really taking it up a notch instead of bringing LTE down a notch. And it's very much focused at sensor messages. It's not an IP data stream like LTE Cat M1 is. I already mentioned the module and service costs. We don't really know what the service costs are going to be. I'm imagining they're going to be very competitive given the market players that they're trying to displace. Vodafone is a big proponent of NB-IoT, if you're interested. All right, AirFinder, I mentioned this as well. This is a real-time location system that Link Lab manufactures and sells mostly to OEMs to integrate location into existing applications, where you can use existing iBeacon type tags. And we're going to talk about a little bit about what an iBeacon is in Bluetooth, or what a beacon is in Bluetooth. And those are read by reader devices that turn around that advertisement data and send it back over long range to SymphonyLink. And then we have a back-end system that takes raw RSSI reports and turns that into location. And I'll actually show that data flow here in a minute. Okay, so now we're into the meat of the presentation. Why Bluetooth? There are certainly other low power PAN or personal area network technologies out there, Zigbee, ANT, and others, which also offer very low power consumption. And I want to be clear that we're not talking about Bluetooth that might be, you know, the guy walking around in the grocery store on his headset talking to his cellular phone. That's traditional Bluetooth or standard Bluetooth. This is Bluetooth low energy, and I'll get into the differences here in a second. But when you couple the ubiquity and the ecosystem around Bluetooth that's been driven by the wide scale adoption in mobile phones, you have a big ecosystem that has developed. So when you couple the large ecosystem of everything from chipset manufacturers to sensor vendors and others with these very compelling power consumption reasons, and you add additional ways to connect to these sensors with a handheld phone with very, very little software work, you get a powerful option for industrial IoT connectivity that you might not have considered. Bluetooth Smart, Bluetooth Low Energy, has been considered a consumer type technology because of its reliance on phones. But what I'm advocating here is that you can use this powerful technology with fixed readers or mobile readers that aren't phones and open up the door on very low power consumption and very low cost sensor or final, the actual thing in your IoT solution. Typical Bluetooth power budgets. I've got some numbers here. I'm going to do a quick calculation just to show you how easy it is to figure this out. Advertising, you'll find out what that is in a minute, at 100 millisecond rate or 10 times a second, generally at about 0 dBm or fairly low power, but not as low as it can go. With 2 AA batteries, get you about 22 months or almost 2 years of battery life. If you slow down that advertising rate to once a second, you can get, theoretically, with nice batteries that aren't going to themselves die in that time frame, over 10 years of battery life off 2 AA batteries. So for sensor devices that need to live for a long time, Bluetooth is really compelling here. I'm just going to jump over to yeah, I will definitely, somebody just asked a question about use cases. I'm definitely going to jump into some use cases as we move forward. So this is a TI Bluetooth low energy calculator. You can see the URL up here. It basically says, hey, pick a battery type. I like AA batteries. 2 of them together give you about 3 volts. Single-ended RF front end, which is typical for Bluetooth. 0 dBm power. You can do -20 or +2. Leave it at 0. Beacon is the use case where you're sending data at this regular interval, which we'll keep here. So we're going to advertise 24 hours a day, and let's say we advertise twice a second or 500 milliseconds across 3 channels, and we'll use 30 bytes, which is a typical advertising package. So there you get 8.9 years. Pretty compelling stuff, and you can play with different use cases, different configurations, etc. But I just wanted to point that tool out. Okay. So let's talk about the architecture. This is really as simple as it looks, meaning that you have a Bluetooth reader device, and I don't know if I can. I'm going to actually try to show you my camera. I know that's trippy. So this is an example of a Link Labs Bluetooth reader device. So this one plugs in the wall, which is nice because then you don't have to worry about batteries on the central device. This receives Bluetooth advertisements and makes connections and then sends it back via Symphony Link. Trippy. So you can imagine anywhere from, I don't know, what does a typical network look like, Mark? Anywhere from 20 to 100 Bluetooth bridges, which each one can connect to I've seen as many as 200 BLE devices connected to a single reader. And there, the challenge is really figuring out, given that the link between this Bluetooth device, the Bluetooth reader, and the Symphony Link gateway is relatively small. We can send about 256 bytes every few seconds as a general payload size. Given that you're trying to shrink down the data that's coming out of these advertising devices at up to 30 bytes twice a second, 10 times a second, you have to have some logic here in the reader device to filter that down. Often an advertising sensor or one that is putting its sensor data in the advertisement packet, that data value isn't changing unless the sensor value changes. So you just have to do some simple filtering and say, okay, every time it changes, I'll send that up. And this is the type of architecture that we use for our AirFinder system, which, again, it's just as simple as it looks. We have this Bluetooth tag. These things are beaconing for AirFinder. What's our typical beacon rate? Like 500 milliseconds, once a second?
Yeah, we slowed it down to increase battery life. I think it's once a second.
Yeah, so 1 hertz beacon rate being read by these readers. That's sending the data back via Symphony Link, which goes up to our cloud server that have an algorithm that can turn this raw RSSI feed into location. And just to put a fine point on it, I actually went on our server this morning, took this little video. So you can see these are Symphony Link endpoint devices on the network transmitting these payloads, which are basically MAC IDs of Bluetooth peripherals and an RSSI value and a timestamp. So you can see some readers see, dozens of BLE packets every interval, and others maybe see 2. So just you can see that's the raw data that we're turning into location on the AirFinder backend.
Got 2 questions here.
Yep. Oh yeah, some people asking. Yeah, I'm definitely going to talk about BLE 5 and Yeah, actually, that's a good question about iOS compatibility. I'll mention that as well. Okay, now let's talk about Bluetooth with LTE instead of Symphony Link. Here, the power of the system is that you don't need a gateway. So the Bluetooth central device can be connected directly back to, for instance, the Verizon network, which can expose a direct IP connection. And when you couple that with power saving mode and extended discontinuous reception modes, you can furthermore have very, very long battery life on the LTE device as well. And I'm just going to quickly explain these power saving modes for LTE Cat-M because I think that they're really important. For a Bluetooth device, that central device connected to LTE, I think it's important to probably be in EDRX mode, which means you're reachable from the network if traffic wants to come down to you, but you've told the network how long you want to go idle in between page windows. And so you can see here this in hyperframes of 10.24 seconds. You can tell the base station, hey, I want to wake up every 12 minutes or something, every 6 minutes, up to 40 minutes, I believe, and be pageable, so that you can be completely idle doing your little Bluetooth tasks, your connections, scanning, reading advertisements, and then come out of EDRX, transmit that data back, and then go back to idle mode from the LTE perspective. And what that gives you is very power efficient backhaul with the ability to run this power efficient intake or Bluetooth connection. PSM mode is taking the LTE connection completely idle, and then you tell the network when you want to wake up. So for devices that don't need to be reachable and might have very long periods of time in between connections or in between data flows, PSM is a good option as well. And PSM is going to be probably more widely available in the early days of Cat-M than EDRX, which is more complicated. Okay, now we're getting into Bluetooth itself. This is not intended to be a deep dive on Bluetooth technology, but for those that are interested in Bluetooth, I think it's important to at least understand some of these basic concepts. So GAP, or the Generic Access Protocol, and GAT is the other important protocol in Bluetooth, Bluetooth Low Energy. GAP, or Generic Access Protocol, governs how devices behave when they're not connected or when they're just advertising. So in a typical Bluetooth network, you have a central device. Actually, in this case, they're drawn over here. You have a central device, which is listening, and you have peripheral devices, and that is your sensor or your actual controller, sensor, whatever the actual thing is, oftentimes, advertising. And you can control that advertising rate. I just showed 100 milliseconds is common. You can go up to many seconds, and it's all a function of the scan problem of how often does the central device see it. So up here you see the peripheral device is just advertising at some interval, boop, 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 boop. And in Bluetooth 4.0, you can put 31 bytes of user data, which is not a tiny amount. I mean, that's double the amount, for instance, of the Sigfox payload. And you put that in every single advertisement that goes out. So if you're a temperature sensor, you can put all of the information you need about what temperature it is, and probably some other data too, in every time you transmit. And you can see that unlike other technologies that transmit constantly from that power calculation, you're not actually spending a lot of battery power to do that. So a very powerful, we would call advertising only method. Bluetooth 4.0 also has what they call a scan response, which is a central device can respond to a peripheral and say, hey, give me more data. And what that allows is a second payload to go out. And this is in an unbonded, unconnected, unsecure mode that can be read by the central device. And you can do 31 additional bytes. Now, Bluetooth 5 allows you to go up to 255 bytes per advertising and response payload. So now you're talking, pretty serious data in just a pure advertisement mode. Some other features about GAP, and you can see it illustrated here, that a single peripheral can advertise to multiple central devices at a time. And so for our AirFinder system, this is very common, where you have multiple reader devices that all see the same tag and use the RSSI to calculate the actual location of the device. So GAP governs advertising and also the early part of how devices bond, but GAT, or the generic attribute profile, is how BLE or Bluetooth Low Energy devices can transfer data to a bonded master device. And so in order to be as power efficient as possible, Bluetooth Low Energy devices are not normally connected. Bluetooth classic devices, like that guy's headset I was talking about, are always bonded, and that's why they use a lot of energy. So what happens for BLE is the central device decides it's going to connect to the peripheral, and it's going to request a certain what's called characteristic. And characteristics are part of what's called services, and services are just standard sets of the way to store data in BLE. And so there's standard profiles and services, like how should a heart rate monitor behave and be readable, and then there's custom profiles, like I'm creating my magical widget and only I know what variables it has, so I'm just going to create a custom profile and not worry about using one of the standard Bluetooth SIG defined profiles. So the central device sees a peripheral advertising, and maybe something changed in that advertising packet. Maybe the device said, hey, I've got new data, and maybe that was embedded in that payload that it sent. And so the master goes, oh, I need to connect to you. And so they bond together, and then the central tells the peripheral what characteristic to send over the air. And it's essentially a server client model using these lookup tables. It's very simple, but you can transfer, fair amounts of data, but we're not streaming data. The data rate of Bluetooth Low Energy is pretty high, megabit per second, but the ability to transfer data, even in this bonded mode, is relatively limited. And you can set different values of a characteristic. You can read one, write one, or notify, basically is the central telling the peripheral that it wants to be notified when a characteristic changes, because this was meant to create this ecosystem of sensors and applications, mostly on phones, that didn't have to be highly integrated together when they were developed, so that you can have somebody developing an app to connect to a fitness tracker without having to do a bunch of low-level coordination. That was the goal anyway. Are there any questions about GAP or GAT as you? I don't know if you go up to like the actual.
There's one question up there.
Okay. So most people look like they're putting in the webinar, which is fine. We may break these out into I'll let you read those and see if you've seen any good questions. Okay, Bluetooth security. So Bluetooth security applies when devices are bonded or when they're doing GAT transfers. When you're doing GAP operations or beaconing or advertising, whatever you send out is readable by everybody. So if you want to encrypt data in advertising, you have to, at the application layer, encrypt that user payload data in some way that somebody scanning and seeing these Bluetooth transmissions going back and forth can't understand. That's really the only way to encrypt advertisement-based data. GAT or bonded transfers are encrypted, but there are some vulnerabilities that are important to understand, because oftentimes the key that's used to seed the encrypted link is sent over the air in clear text. So if you have somebody who's monitoring the transaction between a central and a peripheral, they can pull that key out and then use that to decrypt whatever payload you're trying to send back and forth. So that's the man-in-the-middle attack and the passive eavesdropping method. And those are vulnerabilities if you use what Bluetooth calls the just works method of key exchange, where that key is randomly generated and just sent over the air. And I think one thing that mitigates this security risk is, obviously, you have to be right there in the room on the right channel when that key is sent in order to grab it. So it's not easy, but it's also not hard. So people that are worried about the security of the payload data that they're transferring in a Bluetooth session need to mitigate that. And that's for an industrial IoT system, something to be addressed. Because the headed model of passkey or out of band or OOB transmissions of keys is hard for IoT devices. It's easy on your phone to say, enter this code on that device. And that is what's called an out-of-band key transfer, because the out-of-band is you reading with your eyeballs this key and then going and putting it in this other device. An IoT device that's trying to connect to a central in a factory where there's no people anywhere nearby have a challenge. But I think that's mitigated by the fact that somebody would have to be on site within probably 10 or 20 meters to be able to read those keys out. So it's just something to be aware of. So you can come up with ways of pre-sharing device keys. That's probably a fairly secure way to do it, so that essentially the out-of-band is your manufacturing process of building both ends of the system. Another security feature that I just wanted to mention is identity tracking. And there are a Bluetooth peripheral that's beaconing uses a MAC address that is sent in the clear repeatedly. And unless you take steps using this IRK system that Bluetooth has defined to change that MAC address every 15 minutes, you can be tracked, or that device can be tracked as it moves from device to device. There's all sorts of systems out there tracking people and cars that leverage this identity weakness of Bluetooth. Somebody asked a question earlier about iOS. iOS actually actively blocks the ability of your iOS application from reading the MAC address of a BLE peripheral. Android does not do that, but that's actually a big barrier if you're trying to develop an industrial IoT solution using BLE, because often that MAC address is the identifiable characteristic that you wanted to use. If you are using this IRK mode that iOS advocates, you have to already know how to connect to that device in order to get its MAC address or its true identity. Bluetooth 5.0, there's been a couple questions about it. It was just released a few months ago, and it's, I would say, an incremental improvement over Bluetooth 4.0, addressing a number of the weaknesses of it. For one, it has up to twice the data rate, which just means you can fit more devices on the air. They can talk faster, so there's more room for other devices. And you can also send advertising packets, like I mentioned, up to 255 bytes. So it allows you to move more data in this unconnected mode, which we're really excited about here, because that's something we do a lot of. And there's also more advertising channels and a advertising channel coordination scheme, because Bluetooth was smart to recognize that people want to use BLE to move data in advertisement packets. And Bluetooth 4.0 only has 3 advertising channels, and they can get filled up pretty quickly if you have even a few dozen devices all trying to advertise at a fairly high rate. So they've addressed it there. They've also done some wireless coexistence work to try to mask certain channels in the presence of interference. And they also have some narrower channel bandwidths to give a better link margin for devices that are bonded but at long range. So really looking to address some of the needs of IoT devices here. We're excited to get our hands on some Bluetooth 5.0 chipsets and devices. Some customer case studies. Unfortunately for Link Labs, one of the problems that we have is most of our customers don't like us to mention them by name and wave the flag of their great solution in front of the world. But we work with a number of companies. One is this large US-based manufacturer, and they make these battery-powered devices which have metrics about how they're being used, and they get installed in clusters of 5 to 20 per site. And these clusters are not uniform. They've looked at using mesh technologies, and unfortunately you can build a great mesh there in the cluster, but you can't mesh in between it, which means you needed a gateway in every cluster. They previously had tried to use BLE or Bluetooth Low Energy and Wi-Fi, but what they found out was that the complexities that Wi-Fi brings to the table in terms of provisioning, so you need to get certificates or passwords into those Wi-Fi devices, reliability of the Wi-Fi network, which may be not being owned by a third party, the coverage, and just working with the IT department to get these little IoT devices on a Wi-Fi network has been really hard. So they use Symphony Link as a way to cluster these BLE devices back to a central reader device and then send that back to a Symphony Link device that is itself connected via cellular. Mark's worked a lot on that project, so there's a lot here, and there's a lot of complexity that are introduced when you want to move more data, doing things like firmware transfers and just various types of data flows, not just simple sensors, but connecting with complicated profiles, it can be a real challenge. I do want to mention that BLE or Bluetooth is not the only wireless system that could be used in a hybrid way. Certainly Zigbee or other mesh technologies like XBee, DigiMesh would work well in an environment where mesh will work well, which means you have a relatively high density of nodes that can exchange data and build a mesh. And backhauling mesh data to LTE-M or even Wi-Fi data to LTE-M is a mode to look at. Now that Wi-Fi meshes are becoming more common, and some of the 900 megahertz Wi-Fi, the Halo standard, which we're hoping to see some equipment for in the next year or so. These are other ways to solve that same problem. Just wanted to throw that out there. The more use case data, so this is a little bit more generic, but just places where we see the need for hybrid BLE and SymphonyLink or hybrid BLE and LTE-M devices. Industrial equipment monitoring control. This is generally third parties or manufacturers of conveyor belts, motors, pumps, lights, and other things in industrial settings that need to get usage data out for various optimization, preventive maintenance, et cetera, and need very low cost and long life sensors right on the device, and then can pull those back in clusters to a BLE bridge device, which can be backhauled via SymphonyLink or LTE-M, like I mentioned. Defined area asset management. This is obviously what we're working on with AirFinder, but you can use other, there's other use cases around monitoring cold chains, locations, et cetera, where a BLE hybrid solution works well. Commercial consumables. This is we worked long and hard on that name, but what we see here is customers that are trying to get data about the usage of goods that they deliver on some basis, whether it's CO2, lube oil, air gas, paper supplies, and other things to businesses. Figuring out how those are being consumed and used is a real driver of growth for our company and others in IoT. I've got some SymphonyLink technical information here. I'm actually going to not talk about that. I'm going to answer some questions now. So, Mark, let's see here. So now's your chance to answer some questions. I'm refreshing this page. Most people look like they're asking in the webinar info.
There's two of them.
And there's apparently some others, but okay. So I talked about BLE 5.0. How does BLE work in a noisy environment? Yes. So BLE, Bluetooth Low Energy, uses the 2.4 gigahertz spectrum, and those advertising packages go right on these same, for Bluetooth 4, right on these same three channels. And so in environments where you have noise elevation from motors and other things, it can be a real problem. So it reduces the range of Bluetooth, which is already short, to an even shorter distance. So it's definitely something to watch, but you have a lot of knobs you can turn in a Bluetooth system, whether the beacon is transmitting more powerfully, maybe it's advertising more often. So in an advertising mode, remember, you're sending data 10 times a second or once a second, but maybe the value is only changing every 30 minutes. So I bet you're going to get that value at some point. Noise is going to fluctuate. A bonded connection where you have to need to exchange high reliability, that would concern me more in something like a noisy environment. In terms of industrial grade components, I think you can, I haven't seen a lot of highly integrated complete sensor devices for wide temperature ranges, but certainly the bare components, the chips, the balance, et cetera, can be engineered to operate in that, plus 70, plus 80, plus 85 C type environments. So that's a great question, but certainly one where you would need to make sure that that Bluetooth side and actually the reader side is all engineered to support the kind of harsh environment that you're aiming for. Somebody was asking, do we provide an SDK to inspect receive beacon packets? He wants to encode and transmit small amounts of data. And then process that data. Yeah, that's actually one of the things that we're working on right now, is trying to figure out and working on that SDK to make it easy for developers to do that central-based processing, because we don't want you to have to send the whole hose of data that you're getting from BLE back over the IP network, because it can be costly, especially if you're paying, by the megabyte or by the kilobyte. So would love to get in touch and discuss that more. Maybe we can do that here on the forum and get some requirements so we can make sure that we're targeting those use cases. Does Bluetooth 5.0 use any error correcting scheme in the file layer? I'm sure they do. I don't know what it is without looking it up. I'm confident that they're using some sort of for error correcting, and they use a GF, a Gaussian frequency shift keying phi scheme, so it would be easy to use forward error correcting in that to improve sensitivity. Why does the gap mode consume more power? It consumes more power when it's happening because of all the back and forths between the central and the peripheral device, and also just the processing that's going on there. I don't think it's significantly more, but I'm certainly not the expert. Mark, do you have a thought on that?
Yeah, well, like Brian said, you're maintaining a connection and checking in periodically, so there's going to be some additional overhead from that.
Yeah, the advertising system is really engineered to be as short of time on air, 6 milliseconds on and off, so very power efficient. Talk about management system, not quite sure what that means. Our friend Eric, what options do you have on the Bluetooth end of the Symphony BLE bridge? If beacons or sensor data? Yeah, so like I mentioned, I'm just going to try to figure out what you're asking. If you need to encrypt advertisement sensor data, you have to do that with a pre-shared key that either the central understands or probably your server understands. And you can use creative ways to move that key around. So you can actually use a connected mode to write that key into a custom profile so that your application layer in the Bluetooth peripheral device can use that setting as the AES key or the Diffie-Hellman seed to encrypt the advertising data. So there's all sorts of creative ways to move that key around, which we're happy to get into if anybody was interested. Can I push the data collected from the LTEM bridge to my custom AWS endpoint in the cloud? Yes, absolutely. We leave it fairly open what the IP side of the LTEM device looks like. And we also have some platform integrations specifically with AWS, IoT, and others. Can a BLE central device connect to peripherals? Yes, but also be connected by a mobile device, iPhone. Yeah, that's one of the nice things about centrals is they can connect to multiple peripherals at a time, and a powerful device like a cell phone can actually be a central and a peripheral at the same time. So you can do, I think, what you're trying to say. Yeah, by doing this mode switching. Great. Well, if you have any more questions or any other thoughts, throw them up on the forum and we can respond there. But definitely appreciate it. I would love to get feedback if you want to write in this Bluetooth webinar info thread on the forum what you thought of using YouTube. We used it because it was free. Most of the webinar software out there is kind of expensive, so we were giving this a try. So a couple more questions. Okay. Does each Cat-M bridge require a separate service account from the service provider? Yes, you have to, and each LTEM device has to have its own SIM card and be connected. And we are working on ways to make that easier. But yes, you do need a unique connection with each. Example, battery life at low beacon advertising rate, but including the power consumption of sensor scanning, such as temperature sensor. I don't know, like how much would you think, MCU and a temperature sensor would add to a project?
I mean, you could do it for just a handful of microamps. I mean, it wouldn't be a huge impact, obviously, depending on your particular components and how often you're sensing. But I think you could easily still get several years of performance, something like that.
What is the number of BLE devices that can be sent by various things? It really comes down to how you're processing the data and what you're using for the central and how you're connecting. We start to have issues with AirFinder when we get more than about 100 peripherals per reader. just in terms of all the congestion we see. But I think for some of the backhaul methods you mentioned here, like LoRa, Sigfox, and others, that backhaul is probably a limiting component. If you're trying to backhaul with Sigfox at 12 bytes, that's not even a whole advertising packet unto itself, much less anything else you want to transmit. So that would require you to do even more processing in that central or bridge device. Does NB-IoT not have better urban penetration than LTE Cat M1? He saw a test. Yeah, I think the MCL, or minimum coupling loss, of NB-IoT is like 166 dB compared to 158 dB for LTE Cat M. But there are two things that the M1 guys are working on for coverage enhancement. So basically using processing gain to try to send the same signal multiple times to improve the chances that it was received. But the nice thing about either one of those technologies is that in a way it's kind of the operator's problem to solve. I think at least in the US, the Verizon network is very strong. There's certainly going to be places, underground basements, et cetera, where there's not going to be coverage. And that's why these, bridge gateway devices, why we sell a lot of Symphony Link devices, because the network doesn't exist everywhere. BLE Mesh is certainly available, but you have to basically implement it yourself and use these schemes that we've talked about being peripherals and connected, or relaying advertisements in between devices yourself. And so BLE Mesh, like I said, the only things I've seen implemented are basically roll your own profiles for doing this type of systems. I know Bluetooth 5 is trying to address that, but I'm not the expert. Yeah, Bob's question about energy consumption for M1 reader bridge. It all comes down to how often you're transmitting on the M1 side. The LTE modem, when it's transmitting, is pretty power hungry. We're talking a couple hundred milliamps for a few milliseconds every time it transmits. So if you're able to store data for a long time and then transmit pretty infrequently, you could be battery powered, or use larger batteries. I think for any type of bridge device, or what is technically a gateway, if you can be plugged in or solar powered, you're going to have a lot better time developing your application than if you're trying to make a device that has to work that hard battery powered, but it certainly can be done. And we have, like I mentioned, that battery powered BLE bridge that we're working on is certainly that. Okay, if I see any other questions come up, I'll probably create a thread for each one and take it from there. But I really appreciate everybody's time, and look forward to getting in touch if you're interested in working with us on a project, whether it's with Symphony Link, LTE-M, Bluetooth. We'd love to hear from you. All the best.